In this video, we look at linear momentum and kinetic energy, and we solve some example problems. Kinetic energy is given as this is half mv square, where m is mass of a body or an object. This is the body's velocity. This is the body's speed of velocity. So this is the relationship between kinetic energy, mass, and velocity. Now let us look at relationship between linear momentum and kinetic energy. From this formula, we can write it as, this is, if we square this, to account for that square, we divide by 2m, such that once this cancels this, we're back to this. So this we can rewrite as mv square upon 2m, and this is the definition of linear momentum. So linear momentum is related to kinetic energy with this formula. So it means that kinetic energy is proportional to the square of the momentum and inversely related to the mass. So we shall be using these relationships to solve problems involving linear momentum and kinetic energy. So let's get started. The question number 1 says, two masses of 1 gram and 4 gram are moving with equal kinetic energy. The ratio of the magnitude of the linear momentum is dash. So the formula given is kinetic energy equals linear momentum upon this. So if we represent kinetic energy in short form as K, we have something like this. This is P squared upon 2m, such that if we now from here make P squared subject to the formula, we have 2mk. Making P subject to the formula, we have square root of 2mk. So we now see that P is directly related to this. If we consider only the variables, there is directly related to the square root of mk, where m is the mass and k is the kinetic energy. But in this question, we are told that the bodies, the masses, have equal kinetic energy. So the relationship we'll be looking at now will be P varied as root m. So we can decide to include these two here, but it will finally cancel at the end. So let's use this relationship now to solve this problem. So if P varies as root m, P is the linear momentum and m is the mass. If we remove this proportionality sign, we can introduce a constant. So let the constant be c, so that it will be different from this k, which is kinetic energy that we have used here. So this is c root m. If we make c subject to the formula, we have, this is P upon root m. And of course, as this is constant, the first mass, the constant will be the same as the second mass. So we have that this is P1 upon root m1 equals P2 upon root m2. This we can rewrite. So we can rewrite this to be of this form. So if we write this in the ratio of P1 upon P2, what we have now is, this is P1 multiplying this, so of course this will be roots M1 upon roots M2, such that if we say P1 cross multiplying this, we have the same thing as what we have here. So this is valid for the 2. So P1 upon P2 now will be root M1. M1 is 1 gram. So we have 1 gram here, upon M2 is 4. And root 1 is 1 and root 4 is 2. So we have that P1 upon P2 equals 1 upon 2. And this is just, this can be represented in ratio form as this. This is P1 ratio P2 equals 1:2. So the answer to this problem is 1:2. So the question says, two masses of 1 gram and 4 gram are moving with equal kinetic energy. The ratio of the magnitude of the linear momentum. So this is the ratio of the magnitude of the linear momentum. Let us solve this problem. But before we solve it, if this video interests you, like it, share it with your friends or whom might need it, and subscribe for more updates like this. We post videos on mathematics, sciences, and even technology. Now let us solve the second problem. This question says two masses m and 4m have kinetic energies in the ratio 1:2. Their momentum P1 and P2 are in the ratio. So we still follow the same method we did previously. Kinetic energy is related to linear momentum with this formula. This is P squared upon 2m. And we said that this relationship holds again when we make P subject of the formula. We have root 2mk. And we see quickly that P varies as root mk if we consider the variables. Now, as we did previously, if we introduce a constant, let's call it C, so it will be different from this k. We have, this is C roots mk. So as we have different kinetic energies and different masses, so of course we retain this, so that if we make C subject of the formula, we have P upon root mk. And for the two masses, the constants are same, so that P1 upon root m1 k1 equals P2 upon root m2 k2. So we shall be making use of this to further solve the problem. Now, making use of this formula, this is P1 upon root m1 k1 equals P2 upon root m2 k2, where P is linear momentum, m is mass, and k is kinetic energy. So following from this, we can rewrite this formula as, this is P1 upon root P2. We have something like this. So P2, this will be roots m1 k1 upon roots m2 k2, so that when we do cross multiply, it will be the same as this. So we have not basically changed this formula. So P1 upon roots P2, P1 upon P2 will be roots, the m1 given, this is the first mass, so m1 is m, and m2 will be 4m, following from what we've been given. So m1 is m, capital M, times k1 is in the ratio of these two masses. This will have ratio 1 and this will have ratio 2. You see? So if you have it as this is the masses, the ratio with the kinetic energy. So this is 1 upon root m2 is 4m times this is 2. So that we have that this is P1 upon P2 equals 1 times m is m. So this will be root 8m. So this we can write as this. This is mathematics, m upon 8m. This can cancel, so that we have, so if we cancel m with m, we have root 1 over this, and this is same as saying, this is same as saying root 1 upon root 8, and root 1 is 1 and root 8 is we can have something like this. This is 4. Okay, this is 4 root 4 times root 2. This will give you this root 8. And if that is true, we have P1 upon P2 equals 1 upon root 4 is 2. So we have 2 root 2. Quickly, you now see that the ratio of the linear momentum now will be 1:2 root 2. So the ratio of the two linear momentum will be 1:2 root 2. I hope this video interests you. Like it and share it to whom might need it. Subscribe for updates like this. Do have a wonderful day ahead.